My name is Kees Schakel. I'm the director of Sensing Clues, and within this program, Sensing Clues is the coordinator of this project. Next slide, please. Next slide, yes. So the core of this program is biodiversity, of course. And there's a number of challenges that we will dive into, but our core challenge is to make biodiversity monitoring as near real time as possible, and to also make it more proactive so that insights from the monitoring are useful and can be applied in the field. Next slide. We are working with four reserves, 4 sites spread over 5 countries, and in these sites they are quite big. We have very wonderful species like the bear and the wolf, and icon species like the pelican and the sturgeon. All of them are confronted with problems which are not very typical for these sites, which can be found all over Europe in all Natura 2000 sites and elsewhere. Varying from habitat loss, fragmentation, fire, the quality of the habitats is decreasing, but also things like human-wildlife conflicts, poaching, and related issues. So, next slide. To address these, there are a few problems that almost everyone is confronted with. First of all, mapping and monitoring nature conservation areas is very costly and sometimes even prohibitive. So which has the consequence that it's not done on a continuous basis. It's often not done annually. Sometimes only every 5 or 10 years updates are created. Which means this is the frequency thing. You see that many of the things are, sorry, back to the previous slide. The frequency with which information is collected and analyzed and turned into action is often very, very low. Another thing is that the issues and themes like how to classify things, for varying from ecosystems, habitats, species, but also from region to region, the language that is being used often varies, and taxonomies don't match. So people don't understand each other when they talk about similar things, seemingly the same, but they are not the same, or they might be the same, but people have difficulty finding out that it's about the same. So when you want to combine and aggregate results from various sites and see if there are trends which are bigger than only your area, it's very hard to do this because these standards are lacking and too diverse. The last thing is that many of the monitoring programs are not actionable enough because they are too late with the results. Things already have happened and there was no time to intervene before it was too late. So the now what question is often difficult to answer, but also too late. So what we aim for, as I said, is continuous near real-time monitoring of these areas and provide information that's actionable. And we do that by combining remote sensing images, remote sensing from satellite images, but also from sensors in the field, by combining it with environmental forensics, which is a science focused on learning from traces that you find in the field and that you can attribute to causes and effects, but you actually need to become more proactive and to stop things that need to be stopped, like maybe logging which is going on, and then you have to find out who is actually involved, how fast are they moving, where are they moving, and can we stop them before it's too late, before the forest is gone. The third part, which is very important in this program, is the development of what we call digital twins, which are kind of copies of the ecosystems. And within these, we step up monitoring from just mapping an area into monitoring it, from periodic monitoring to near real-time monitoring, to also forecasting how things are developing. So it becomes predictive. And with using this predictive information, we can also prevent issues before they occur because we've got time to intervene. Next slide. So we map the ecosystems and the species, we monitor them and detect changes in near real time, and we detect the changes and events that are occurring in the various sites. And we do that across the different languages that are being used, literally, like Romanian language or Ukrainian or English or French, but also the standard languages that are characteristic for labeling, for example, habitats, across area boundaries so that we can aggregate insights and learn across different sites, and of course the language barriers. And of course, and that's the most important thing, we are very practical. It needs to be tested and it needs to be ready for the field. So what we are developing and what we are going to show you today is a first public example of the things we develop. They are TRL-wise at a very high level, ready to use and tested in the field. So once the project is finished, and maybe even already earlier, the technologies that we are developing are available for Natura 2000 area managers, researchers, but also analysts and other stakeholders, policymakers that are interested in working with biodiversity related information. Thank you very much.
Yes, then I will take over from you, Jan Kees. Hello, my name is Melanie. I work as a geospatial data scientist within Nature First, and I'm going to present to you the topic of the ecosystem base map. So please go to the next slide. Just to give a very quick introduction. So with this ecosystem base map, we're really trying to get a complete picture of natural areas. Our areas of interest are mainly Natura 2000, and we want to make use of all the environmental data that is available at the moment. There's a wealth of information, but to really make it actionable, that's what we're going to try to do with this base map, because we keep in this base map all different map layers, which together constitute building blocks for actionable products. So we make these layers available so that they that we can create value that can be used directly in the field. So let's go to the next slide. A quick look into our Nature First areas of interest. We see here the spatial boundaries of our 4 field partner field sites. In Spain, Romania, Ukraine, and Bulgaria. And so here we see outlined the areas for which we are collecting this environmental data. Each of these are Natura 2000 site, and we try to make this all very generic so that it can be applied to any Natura 2000 sites if we have the boundaries like this. So now let's go to the next slide for the first version of the ecosystem base map as we have it at the moment. So here you see the data for one of our field sites, which is Maramureș in Ukraine and Romania. And we have here in this picture 9 layers available, but actually in total we have 18 layers in these 3 categories. We have elevation data in the first row, satellite bands, which is from Sentinel imagery, and we have satellite indices. So these layers are all globally available, so we can create this eco base map for any area in the world. But right now we have this available for our 4 field sites. And I want to take a little bit of a more in-depth look into some of the layers. So let's go to the next slide. Here we are looking at the DEM, the digital elevation model. So this is height data for Maramureș. In the case of Maramureș, we see we have height varying from 500 to 2,000 meters above sea level. And in this case, we're looking at static data. This doesn't change in the near future, but very important information for many of the products that we are thinking of creating. Because it influences many things such as species abundance, species distribution, people, where they walk. It all is connected to this digital elevation. So it's a very important layer to include for us. But maybe more interesting is the next slide, we also have in our eco basemap dynamic layers, which means that these layers change over time. So here we're looking at the normalized difference vegetation index, which is really a greenness feature. And it shows the level of vegetation here, in this case, in Maramure's area. And as you can see, this is dated for March 2023. So this layer will be updated throughout the year, and so that you always have the latest information available, because of course vegetation changes over time, changes throughout the seasons, and we also would probably like to track this change. So we make sure that in the eco basemap we have the latest information available, but also keep an archive of all the information we have collected before. So this is some examples of what is in this eco basemap, and then I would like to present to you a few of the ways that we are thinking of using this in terms of for the field partners. So go to the next slide, please. So here, one of the solutions that we have implemented before within sensing clues, but not yet for Nature First, is a risk and suitability mapping. So in this case, you see here on the right side probability map for illegal activities in an area, illegal human activities. So we try to establish a risk, and we do that based on all the layers that are actually currently available, these environmental layers, in the eco basemap. So though this map is not created for our field partners now, we will be able to do this very easily once we have observation data of illegal activities in our in the areas of Natura 2000. And so it's all built on these input layers in the basemap. If we go to the next slide, another case where we can use all of the layers is in habitat mapping. And I just want to give a teaser, because this is going to be explained to you in our next topic. So I'm not giving anything away in terms of the end result. But similarly, all the layers are used to model and create the habitat mapping. And this can be done in a very automated way for any area that we want to collect data for. And then we go to the last slide, where so Jan Kees already briefly mentioned the digital twin that we are working towards, and the eco basemap really will be a starting point there, and provides a lot of information into the digital twins, which could be very useful. So the way I like to see it is that you walk into the field with your app, and you're collecting data, but at the same time you will be able to request all of the data that is already available, such as where is the nearest river in my area, where is the nearest forest, how large is the nearest forest, and then build on top of that, what is the risk of me encountering a poacher here, or an elephant, or what is the likelihood that I encounter an elephant. So all these things hopefully will be available to you in real time, and the basemap forms really a foundational layer to retrieve this information. So thank you for listening, and we can go to the next topic.
Well, I think it's me. I'm Boris Hinojo from 3Data. I'm going to talk about the habitat mapping method. Next slide, please. Well, I start from scratch in this topic. We have some previous developments. And for Nature First, regarding this habitat mapping, we established like 3 objectives for the project. First of all, through use of remote sensing, trying to generate the habitat map for a protected area, and in this case, testing it in our field sites. Second, we want to assess the changes in these habitats, so we want to create a tool to assess them using remote sensing technologies. And the last objective will be try to obtain some parameters and variables regarding these habitats to help us to assess the conservation status of these habitats. So these are our objectives. Next slide, please. Since we are very ambitious, we plan in Nature First to map the 5 field sites from Spain, Romania, Ukraine, and Bulgaria, and it's almost 30,000 square kilometers. It's a huge challenge in the project, and we will try to make it a reality and to test the habitat method. Next slide, please. And for that, we are creating a generic model for habitat mapping for classifying images. And this model has, well, 3 main components. First of all, are the training areas. Since we are using a supervised classification, it's the same that we are using ground truth control points in order to know and to show the algorithm which classes of these habitats are in the land with these images. So these training areas are a key element of the classification model. And the second one is the second component is the images. We're using Sentinel-2 images, satellite images, because we have these images for all of the field sites. But the generic this classification model can use also high resolution images from other satellites, from aircrafts. Images from ortho images are also from drone images. So this is relevant to use in this model. And we also are able to classify single images or pair of images, or also seasonal images, for example, 1 image per month, to improve the classification of the protected area. And the third component will be the classification tools. Thanks. This is the raw classificator that we are using a machine learning model. Also, we introduce some tools, for example, for correcting classification errors that we can correct using thematic layers like rivers, altitude maps, or lithology maps. We are able also to maintain the coherence between maps using also thematic layers that urban areas or roads or this kind of infrastructure that we can include in this classification model. And this is relevant for maintaining this coherence between maps and cartographies. Also, we are able to, with this generic model, to add some specific rules for the area or for the region or for a protected area in order to create more specific model for this protected area or region in order to improve the classification or the map. The last would be the capability to obtain and save some intermediate results in order to apply them after the classification is made to obtain parameters for conservation status or assessment of the conservation status of habitats. Next slide, please. So this is the process for our habitat classification method in a nutshell. It's like the first one. We have a square of 10 kilometers to classify. We have the second, the Sentinel images. The third part will be use and create these training areas and that we can integrate in the SenseInclude platform and go into the field with the mobile app to ensure that we are using correct training areas with the correct habitats using EUNIS classification. Then we have we can run the model. This is part 5 and 6, and we are doing some refinement, generalization to obtain the final map for the habitats. And well, this final result, the habitat mapping, we are using EUNIS classification, and after that we are assigning habitats of community interest is very relevant because well, it's required for the EU legislation to assess the conservation status of this habitat. And it's also a very relevant tool for management the protected areas for the managers of this Natura 2000 network or other protected areas. And it's also very important also for the permits or that is needed for some uses or activities in the area. And next slide, please. So we have developed this first version of the generic model for habitat mapping, and since we have also obtained the training area for Ancares Corel, we can now show the results. Next slide, please. For this protected area for Natura 2000 network in Spain, northwest Spain. So this is the map that we obtained from running this generic model for our habitat classification. Next slide, we can look at it in more detail. This is to the left the sentinel image that we are classifying, and to the right we have the result of the classification with the EUNIS classes and all the polygons drawn for obtaining this habitat map. As you can see, Sentinel has this spatial resolution of 10 meters, 20 or 60 meters, depending on the band that you are using. So if we can show in the next slide with more zoom the results, please, the next slide. Please. We can look at the results with in the background with a high resolution image taken from Google satellite with less than 1 meter. You can see how the polygons are drawn in through this classification. I think we are proud of these first results that we obtained classification this site. And to the right, you can see some intermediate results that we want to explain that we have some small polygons inside other polygons that are the final result for the habitat mapping. And this data is maintained and can be used for assessing the conservation status of the habitat. In every polygon, we have the EUNIS classes from 2012 or 2021. We have these taxonomy crossovers that in the data model of the project with the knowledge graph that we can convert to different kind of habitats, even the country list of habitats, like the Spanish standard list of terrestrial habitats or others. And this is, I think, very useful for managing purposes. Next slide, please. And well, our next steps are integrating this habitat mapping tool in the SenseInclude platform to run it in all the field sites. And we want to establish also now the training areas in the other field sites with the collaboration of our field partners in the Danube Delta, the transboundary area of Mara Mureș in Romania and Ukraine, and the Stara Planina in Bulgaria. These are three different, very different landscapes, and we are running this the same generic model to assess and to classify and to obtain this habitat mapping. And also we want to generate these specific rules for every field site. And after that, in the medium term, trying to create this tool for habitat changes detection and to also automatic update the training areas. That is also a very key issue in this term. And that's it for my part. Thank you.
Judith, you're on mute still.
Mute. Sorry, I'm on mute. Good afternoon. I will continue. About camera trap images. So please go to the next slide. So the field sites of the Nature First project, but also many other nature conservation organizations use camera traps. And often they are used to monitor biodiversity. And these camera traps provide many, many images, and they take a lot of time to check and annotate manually. Therefore, within the project, we provide a solution to automatically process images with artificial intelligence. So what can artificial intelligence recognize on these images? Well, first of all, they can recognize human and vehicles like cars and motorcycles, which can be useful for illegal activities. But of course, they can also recognize animals and their species specifically, and they can count them. And even very advanced models, they can recognize individual animals. This is, for example, very handy with big cats because they have a specific pattern on their fur and the model can recognize the individual itself. The models are also very efficient because camera traps usually react on movement, which means that if you have a camera trap somewhere, it often takes a lot of pictures of what we call waving grass. And that can be up to 70% of your pictures. And if you have to go through all of these images manually, that of course takes a lot of time. And the AI will ignore those. And with this solution, you can work with multiple users on the same image set at the same time. Next slide, please. So how does the process work? Well, first of all, of course, you have to upload the images to our platform. And once they are there, you can run them against the AI models or annotate them manually with a tool called TrapTagger. And TrapTagger is a solution which is developed in South Africa, and it's open source software, and it can be used by everyone for free. And once you have annotated your images, you can export your results, and we import them in our platform again, so they can be used for analysis and reporting. Next slide, please. So how does the annotation work? Well, besides the advantages of removing the waving grass images and working with multiple people at the same time, there are more advantages. Because if an animal passes a camera, you normally get a few pictures of that same animal, maybe 4 or 5. And if you have to classify them manually, you of course have to go to 5 pictures. But the model will recognize that they are all the same animal and puts them in a cluster, and you only have to classify them once. Also, you can use custom labels and hotkeys, which means that, for example, if you have a lot of elephants in your images, you can just use the E for elephant and classify them very fastly. You see in the table below, that's an example of a test that was done by TrapTagger. You see 3 rows. So the first row gives some details about a classification set that was done completely manually, so without any artificial intelligence. And the second row is AI aided, which means that the AI models classified most of the images, but the ones where the prediction was not too good, they were sent to a human in a web interface to be classified manually. And the last row you can see that was completely classified by the AI model. And you can see that in the time column that it really reduces a lot of time. It goes from 320 hours to 5 if you start using the AI models. Next slide, please. So this is an example how it looks if you have to classify something manually in the system. So on this picture, you see a lion which has a bounding box on it. So the AI model creates bounding boxes around the animals so you can easily identify them and classify them. So here you see a lion, and in the case of this example, you could maybe use an L as a hotkey to classify lions. On the right side, you can also see how the classification works. So you see some examples, but you also see the option to say nothing, which means that there's actually not an animal on the picture. And below the picture of the animal or of the lion, you see 3 small dots, which means that actually three images were taken of the same lion. So we consider this to be a cluster. And you only have to annotate once and say it's a lion, and the model will understand that the other 2 pictures are also lions. Next slide, please. So how does it work if we export these results and import them again in the SensincLues platform? So here you see an example of the same data, but now used in our web application, which is called Focus, and where you can combine data that you have collected. And here in this example, you just see one example of one image that has been classified, and you can see it on the map. So you actually see where the camera trap was located, and you can see which animal was on it, the classification on it, of it. And if you want to, you can click on the image and you can see it again in a bigger format. And with this tool, you can do all kinds of analysis because there are lots of filters options. So you can filter, for example, on time, on location, but also on camera trap or on a specific animal like a lion. Next slide, please. And there are more advantages to import the data again in the SensincLues platform. And that is because we combine all the data collected. So it's not just data from the camera traps, but it's also data that you collected, for example, on a mobile application from SensincLues, where you can register observations in the field. But also the ecosystem basemaps that Melanie just explained are in there. And all this data together, you can use for data analysis, for reporting, but also for the risk map and the digital twins that Melanie also just showed. Next slide, please. So what will we do? What are our next steps? So first of all, we are now testing and building a connection between TrapTagger and the SensincLues platform so we can actually import the data correctly. And then we will run some pilots with the Nature First project. Of course, we are going to also implement some improvements, and that's specifically related to the European memos, which are very important for the Nature First project. So we will make sure that there will be a good classifier to recognize these animals. Also, we will make sure that the model is able to better classify in difficult circumstances. For example, when there is bad light or there's much difference between locations. And the last thing is that we will improve the method to count animals. Thank you.
Okay, then I will take over. I'm Alvin from Semantic Web Company, and I will talk about taxonomies and crossovers. Before I go into the details, this is a slide about why. So why taxonomies? And this actually summarizes what Kees said in the beginning. So if we don't have a shared definition and understanding of concepts, that means that the monitoring becomes expensive and time-consuming. And also, analysts spend 80% of their time on data engineering instead of doing the analysis. And also, as regards to the monitoring, we will have like low frequency because some things will not be hit. So some species, for example, and we have also high latency because the time to the actionable insights will be longer. So ultimately, we will have, in the end, is that protection measures are reactive and too late, and in the end, the biodiversity decline is not stopped. Next slide, please. So what if we have a taxonomy in place? So taxonomy-related solutions. So that means that we will have a unified language of taxonomies and their crossovers. And that means that 80% of the time, the data analyst will spend on the analytics instead of the data engineering. And as regards to the monitoring, we will have low cost and near real-time monitoring and reporting routines. And now we will have things flipped, where we will have high frequency and low latency. And ultimately, we will have create actionable and timely insights as regards to the business intelligence. That's very important. And in the end, we will have the biodiversity decline that is reverted. Next slide, please. So what you see here is the Habitats UNIS 2012, which is already provided in a graph format and which we have imported into the pool party. And now you see a visualization of it in graph view. So you see like a specific habitat, which is selected, and on the right, you see all the attributes related to that habitat, like the name, the code, and all the context, like what's the broaders and the narrowers and so on. So we have reused all this information by keeping the information as it is with some, minor changes. And there were also other versions of habitats from UNIS that were introduced later on, like the 2017 and 2021. So in this case, we have imported those as well. And because the codes have changed, but also the name of the habitats have changed, we have used the crossovers to make the alignment between these taxonomies. So we said, okay, this concept in the 2012 version is the same as the one in the 2017. And for this, we used these spreadsheets that were generated by the experts. So in the end, we have a source of truth, which is the 2012 version for UNIS, and then interlinks to the 2017 and 2021 versions as well. So the aim is that all this data in a graph format to make them accessible to the public and machine readable for researchers and developers. Next slide, please. So here, what you see on the data level side, so we have the blue node, the circle which depicts the UNIS 2012, and the red one is the habitat from 2017 and 21 respectively. And you see that now we have the exact match relations between those and the one which is the 2012, which is the source of truth. So this means that even though these habitats might have a different name, but they semantically mean the same thing. And so this will be interpreted both by the machines and by the humans in the same way. And I just want to mention that not only exact match relations are generated because some of the habitats are like approximate, and then we use like close match relations or broader or narrower and so on. So in the end, we can use any version of these habitats taxonomies for reporting. So we can use 2012, 17, or 2021. Next slide, please. So let's say a few more words about the the taxonomy linking, or what we call project linking, aka crossovers. So the project linking is the way to create linked open data where concepts in a project or taxonomy are linked to concepts in other project taxonomy via relations such as exact match, same as, or even bespoke all properties such as habitat type. So this means that using these relations, we can link habitats, and this also adheres to the linked data principle. So if you look at the linked data principles, these are all the principles that are laid down by the Tim Berners-Lee on how the data should be there, how you choose URIs, how to reuse the data, and how you link it. Next slide, please. So here we see the project linking, which now we don't have it between the habitats, but we have a cross domain between habitats and species. And for this, we have used a spreadsheet from EUNIS, where it tells you, like in this habitat, which are the diagnostic species, so mentioned like in text, and which are like constant species and so on. So we use this information and we tagged those. So we have NLP techniques which we can call, and then from those texts, we get the URIs of those species. So once we get the URIs of the species, so we go from text, from strings to things, in other words, then we can create the connection between the habitats that you see on the left and the species that you see on the right. So you have a URI to URI matching by using a relation. Next slide, please. So this is the current crossover of the knowledge graph we have created so far. So on the middle, you have the habitats, the 2012 version, which, as described before, we said we have the mappings to the 2017 and 2021. But on top of that, we have the relations to the species, to the Korean land cover, and also lately we included the Natura 2000 sites, which also have in turn the connections to the habitats and to the EUNIS species. So you see everything is interlinked now, and we can now answer questions which we could not before with data was in silo. Next slide, please. So here just we see which kind of information that we use. So you see some of the information that was out there was already in graph with RDF format, but some of it was in Excel. And even we have shapefile for Natura 2000. So we also have the polygons of these sites, which we also exploit and convert to the RDF. Next slide, please. And to bring this Excel data or non-RDF data to RDF, we use unified views as a data wrangling tool, which then converts everything into the graph RDF format and then links things together. Next slide, please. So now that we have all this information linked, then we can ask questions like this. So I'm going to just mention two or three. Like which Natura 2000 sites contain species that are declining, in which land covers can little owl be found. And also we can have things which go beyond that, like you see things in the recommended system, like which species can also be found in other habitats based on typical species they have, or can a bear be attracted to certain habitats based on the species that are relevant to the bear. So all these things now can be powered by this knowledge graph that we have created. Next slide, please. And this is the query that we have put, and now you can get similar information now that we have everything in a knowledge graph. So here you see a query like, give me all habitats where Athena noctua lives, and the habitat has natural grassland Korean land cover. So you can achieve this by just picking the facets on the left side, and then you get to the information. So you see here we have 4 habitats that fulfill this all these criteria. Next slide, please. And also in the end, I just wanted to show you that we also exploit the shape files, so these polygons. So from the polygons, once we have created the RDF data, now we can create adjacency relationship between sites. So we can say this site is closer to this one in a semantic way. And that means that we can ask questions like, which are the most common species that exist in sites adjacent to the site that you have there, like PLH 020044. And then you see the result is on the left. So from that site, we have these 3 nodes that are the species that are the most occurring there. So in the future, we want to visualize that kind of information and also enrich our knowledge graphs further on. So back to Jan Kees.
Thank you, Albin. It is a little bit of a technical story, but I hope you all also hear the potential of it. I will give a few more details about the nature first knowledge graph. So as explained in all the presentations before, it combines the habitats, the locations, but also the species and the human influences that are all present in one site. And it is not only describing what you can find, but it's also containing the metadata. So the metadata is the descriptive data where the data came from, describing the authoritative source, the age of the data, etc., which is important to understand and value the information of the predictions that come out of this. If your satellite images are 5 years old, then of course you still have this environmental observation from the NDVI, for example, but then you know it might not be very trustworthy because it's already 5 years old, or it is an image from spring and we are now in wintertime, so we would like to work with wintertime images. So the combination of the metadata allows you to much better understand and use the observations that are there, and they are all combined in the same graph. The graph also helps us to kind of get rid or solve all the difficulties that people have when they are data engineering data sources from many different kinds. So people have images from ChemTraps, you've got satellite images from satellites, but we have also human observations, sometimes in the form of a spreadsheet, sometimes in the form from an app that people are using, and so many other forms of data are being collected. The knowledge graphs allows us and is a very powerful way of linking all those different sources, independent of the structure and independent of the format of that data. So another part is that the knowledge graph, as explained also by Albin, is able to explain the story, as so to speak, to you in your own language. Because the knowledge graph is multilingual, it can be presented in French or Spanish or Ukrainian, but it can also be used in different classification systems. So the systems that Albin, for example, explained were EUNIS classes, but there's also there are also classes, habitat classes, defined by, for example, the IUCN or by the WWF, which are slightly different or sometimes entirely different, but similar, but not the same. So to make these crossovers, it's very important to have a knowledge graph like this in place. And with the knowledge graph in place, you can ask all these different questions and browse and search and discover relations between sites, between species, between densities and other questions across domains in the sense of biologists and ecologists, but maybe also some other fields like land use planning, and also from organizations. Because in nature conservation areas, a very typical case is that you will find many different organizations having responsibilities in the same area. There's a water authority, there might be a forestry authority, there's environmental authorities, and there might also be economical activities governed by the Ministry of Foreign Affairs or Internal Affairs or whatever. So the knowledge graph allows information sharing and communication across these domains and organizations. Next, please. So back to why it is important. It's the knowledge graph enables you to answer questions in a very easy way, and to answer questions like, well, while you are in a certain habitat, then what is the relation with the red species list, for example? Which of the species of the red list are frequenting this particular habitat. And a very nice example that Albin was explaining, the habitats adjacent to this area, do they show or do they habitat the same species, or are they not yet there? Which might be a policy indication for creating corridors or taking other measures to link fragmented nature areas so that the species can find its way to the other areas. So the tool is very important for protected area managers, but also for policymakers, researchers, and of course, a very emerging theme is the use of citizen science, which is a very powerful way of collecting data. For example, birders and other nature lovers who walk through the nature reserves, they see lots of things, usually wildlife sightings. And these reports can also be used to feed the knowledge graph, which in turn feeds the digital twins, the habitat models, and so on. Next, please. So we are developing high-end technologies for very real-world concerns. And these concerns are all related to the biodiversity spheres. So there's a loss of biodiversity, it's just a big problem, there will be no debate about it. Habitat is lost and fragmented for one of the reasons for fires, which might be spontaneous, but sometimes also not. And when big animals like the wolf and the bear are living in an area adjacent to or within human-dominated landscape or adjacent to villages, then you also often see that there are human-wildlife conflicts. So the information that we are collecting and which we are embedding in digital twins is used to create early warning systems so that these conflicts can be reduced and can be kind of mitigated in a way that people and wildlife can coexist. And of course, poaching is also a serious issue. And as explained earlier in the presentation, we are also using environmental forensics in this program to use the insights from the forensic science to understand poaching much better, to attribute it, and to find the culprits, so to speak, to catch the criminals, but also to find out if we can define measurements to prevent poaching from taking place. Next slide, please. The problems that are in between those solutions and the people in the field in the past were that they were very, very expensive. So with this program, with Nature First, we aim to make them very, very affordable. And then we talk about tenfold more affordable. We also bring things to near real time. We say near real time because some of the things are really in real time, but some of the things, of course, are not very relevant to make them in real time. Like the digital elevation model, it doesn't make sense to update it every day. One time every 4 years would be enough. While the NDVI index, for example, or the moisture index, it would be worthwhile to do that every month. While the weather forecast is something that we would like to have every day. And when something is happening, like a fire or a poaching incident, then we would like to have it instantly in real time. So the other problem that we address is these translation services, as I kind of summarize them, which is making these crossovers in languages and taxonomies, which allow people to discuss themes and biodiversity policies across domains, across areas, across species, and make them actionable. So that is a very important thing. Last slide. Last but not least, all these things are being developed as we speak, but also used as we speak. So testing is going on right as we speak. What Boris was showing is real work that was carried out in the last few months. And the data that he collected from the field sites was collected with the handheld app that we have developed and modified specifically for this purpose. And also the basemap layers that Melanie was showing are the first edition from it have been presented this month, just a few days ago. And likewise, the crossovers that Albin was showing are available on our website and can already be used by researchers and developers through APIs or directly through the website. So thank you very much for your attention. and we are looking forward to go in to listen to your questions and to hear your feedback, to learn what you find most interesting, what you find most challenging, and maybe you would like to work with us already on some of the teams. Then, of course, this is an open invitation to all of you. Back to the presenter, the moderator.
Thank you very much, everyone, for your presentations. I already saw some questions in the chat, and I will give the opportunity to everyone to unmute themselves if they want to ask the questions themselves. The first one was from Baki, and it was for Boris, I believe. Baki, are you still here? Do you want to ask?
Yes, I'm still here. I noticed that I should change my name. My name is Kees. I was wondering about the granularity of the area cover that you try to classify. How big are those, and how many classes into how many classes do you classify the areas?
Okay, thanks, Phil. We are using for classifying the pixel-based classification, because we are using Sentinel, and for this size of pixel, we obtain better results than with object-based. We have better results if we are using, for example, world view images with high resolution, if we are using object-based classification. So for the classificator and how many classes are we using, it depends on the cell that we are classifying. So I think more or less we are for this area of this Ancares Coral is more than 100,000 hectares. We have classifying 18 classes with this model, which is algorithm. So that is the result. And the other classes we obtain through rules, through thematic layers or other specifications that we included in the model. So we can reduce the classes to run in the classificator. So that's it.
Okay, great. Thank you.
Welcome.
Thank you. I also saw that Jose had multiple questions.
Yep. Hello. Yes, thank you very much for the invitation. Very interesting. We are highly active working in a very similar topic in a nearby region, also in the north of Spain, in the region of Cantabria, and now expanding a little bit towards the whole mountainous range with the people of University of Oviedo. So the questions are multiple because we work in a very similar topic, but I just wanted to focus a little bit in the first, the EUNIS level you are using for, but you explain afterwards. So more or less I have it clear. But we found the problem when we go to the field with our botanists and we find different levels when collecting the in situ data. Sometimes you can go deeper. Other times you can reach a EUNIS level 4, 5, or even deeper. So at the end, when you have a big database, we, after being 4 years collecting information, we found like a little nightmare that had to homogenize for running the models. Otherwise, we are not absolutely, we have not the certainty that a specific point remains for a particular category. So how did you do that? You have a previous clear classification and you started sampling just following that scheme, or you found some kind of noise when homogenizing the in situ information? First question.
The different levels that we are using, EUNIS, I think, Jose, for the question.
Yep.
Our range of levels that we are using is from 1 to 6, yes, because in the field you have, like you said, you are finding different EUNIS classes. Maybe you have very interesting data to work with it, or maybe not. So you need to adapt to these levels in order to be able to classify all of the protected area. So that is our way to doing things. We have some previous data, in some cases, in order to help us which EUNIS classes we are present in the area with which we are going to work. And if we are going to classify every classes or not, because some classes is maybe not necessary to use in the classificator. So we can introduce them through rules and other tools in order to use the classificator in the most important and relevant things to help us in our work. So that is our approach in this issue.
Yeah. Okay. Yeah, it's a complex issue. How the important thing is having like a workflow or a decision rule on how proceeding. Now, what we did was to homogenize everything up to a level 4 and work on that in the whole Cantabrian range. And we have that classification scheme already discussed and fixed. And maybe could be interesting one day to talk about that, because more or less we could share similar vegetation types. And the next questions are really related with this. Is once you have a classification scheme or habitat list or whatever, you have to fix a number of classes. Sorry, a number of points, a number of regions of interest, and a number of locations for collecting data for that habitat type, covering the geographical gradients, the entire study area, and covering environmental gradients, all the abiotic factors on which the habitat distributes, for avoiding truncation of the geographical distributions. So that's a very important issue that also affects afterwards individual predictions when putting all together for creating a continuous vegetation map and avoid misclassifications, overestimation, underestimation, that you classify one habitat type over another habitat type that you have not sampled, but it's still there and it's quite similar to the one that you modeled. So that's a very complex issue, but just to, if you face this, how did you solve it?
Yeah, the thing is we are running a different the model, but we are model different classificators within every cell of 10 kilometers per 10 kilometers. Every time we are using that, and we are incorporating these thematic layers, rules, and the training points for every UNIS classes in these cells. So this helps us to avoid these problematic issues within very large areas for mapping these very large areas. Because if you're trying to map very large areas with the same classificator, you're going to find those problems.
Yeah, okay. Thank you. Very, very interesting and very clear and clean approach. And I enjoyed it a lot, and a lot of discussions maybe that, Boris, we will see sure in many other arenas. And thank you very much.
Yeah. Thank you, Jose.
Thank you. Unfortunately, we don't have time left to go to other questions, but Daniel, we noted your questions, and we'll make sure that to connect you with the team members from Nature First, and that your questions are answered.
Okay, thank you. Congratulations for the presentations. I found them very interesting.
Thank you. And yeah, I would like to leave the floor to Judith.
Yes, so with this, we will close the first demonstration of the Nature First project. Thank you all so much for joining this session, and we hope we keep in touch and that you join the next demonstration of this project.